when you graph these, you are responsible for the graphs here. You've got position versus time. So this is going to be the position graph versus time, like I said. And if I take this and I displace it to the right, giving it some positive initial position. So I give it some positive initial position right here at 0 seconds, and then I let go. Well, what's it going to do? So it's been displaced to right here. And then I let go, it's going to go that way towards equilibrium, and it's going to speed up. All right, so it's going to speed up. Okay? And then right here it's at 0. The position 0. And that's where its velocity is maximized. Notice, remember that velocity is the slope of a position time graph. And here the slope is 0 because it's stopped. At maximum amplitude, it's not moving. It's turning around. Or in this case, I'm just letting go of it. And then it has its steepest slope as it passes through the equilibrium position. And that makes sense. It's moving fastest right here. And then it goes through, and it's going to stop over here, this point right here. It's slowing down now as it moves over to this point until it stops. And then it's stopped right here, and this is where it turns around and starts to come back the other direction. Now it's passing back through equilibrium. And then it comes right back to where it started, right here. It says its starting position. And then it does that all over again. And so on and so forth. So as time goes on, this thing's moving back and forth. Okay, a few things on this graph. This maximum displacement is the amplitude. Again, amplitude is maximum displacement. It can be positive or negative. The time it takes to complete one entire cycle to where it goes to the left and back again, that is the period t, right? Uppercase T. Now, I also want you to notice that it can have some displacement other than amplitude. For example, if I look at this place right here, that's just some value of x at some value of t. And x could be positive. X could be, say, if you're right here, you could have a negative x. Okay, so x isn't always amplitude. It can vary. Now, given this graph right here, I want you to notice that this is a cosine curve. All right, it's a cosine curve, not a sine. Sine starts here. This starts up here. And so the relationship between x and t is written like this. X equals a times the cosine of omega t. All right, a represents the amplitude. X is the position at any point along this, all right? The position of the spring at any point relative to equilibrium, okay? So at, for example, time t, say t is right here, then that would be its position. Say t is right here, then that would be its position, to be some positive value. If t were over here, its position would be down here, okay? Omega is called the angular frequency. We've used angular velocity before for something going around in a circle. When we talk about oscillations and simple harmonic motion, omega, or omega, lowercase omega, is referred to as the angular frequency, and it is measured in radians per second. So be careful, you have to be in radians, not degrees. You have to be in radians when you're dealing with these equations, not degrees. Now, one other thing, I want you to remember that omega is 2 pi all over the period. Remember that one entire revolution when you're talking about circles, and this is also true for one complete oscillation, is 2 pi radians over the time it takes to complete one oscillation or one circle for a circle. 2 pi radians is 360 degrees. All right? So one entire cycle is 2 pi radians. Even if you're just going back and forth in harmonic motion, we still use 2 pi radians for one complete cycle. Over the time it takes for one complete cycle, from here to here, right, one complete cycle. All right, that would be one time for it to go to the left and back again to where it started, right over here. All right, 2 pi radians. 2 pi radians, and over time period, lowercase t, right? And also remember that period is the reciprocal of frequency. So this equals 2 pi f. I would just want to say that because sometimes you'll see this written as a cosine 2 pi f times t. We usually put that in parentheses. Okay. Now, the next thing we're responsible for is the velocity time graph. So let's just continue this down. Velocity, and we're also going to look at the acceleration versus time. Now, what is the velocity at the very beginning? Remember, this is all about the slope of this graph. The slope of that graph is 0. Also, you can tell I'm holding on to the block. I've moved it over here. I pulled it over to some positive position, and I'm holding on to it. And then I'm going to let go of it. So it's displaced to the right. I'm saying to the right is positive. And then I'm going to let go of it. It's not moving yet. Plus the slope of that is 0. So that's 0 right here. Okay? Slope of that 0, that's 0. That's 0 velocity when I let go of it. And then look at this point right here. That's where the line is steepest right there. So that's its maximum speed, but the slope is negative. And that's because it's moving right through here to the left. And to the left is negative, according to what my convention. And it's going fastest right there. I'm going to drop right below that to some negative value right down here. Right there. Okay? That point right here is a negative velocity. It's below 0. And that represents the slope of that. It's negative velocity. And then it gets back over here. And notice it stopped again. That's when it's got all the way to the left and it's not moving anymore. It's going to turn around. It's turning around. Slope of this is 0. So right below that, I'm going to go back to 0. And then it comes back again. And it's passing to the equilibrium position to the right. Over here. Equilibrium is along the 0. This is 0 on the x-axis, on the position. At that point, and it's going fast, it's positive, steep positive line. So that would be a point about right here. And now it's come back to where it started, right over here, and it's stopped, and it's turning around again. So that's 0. So that's back down to 0. So now look what this looks like. This is a sine wave. Although notice that a sine wave is normally up and then down, so this is the exact reverse. So the equation for this, which for you calculus folks is the derivative of this with respect to time, comes out to be V equals negative, because this is an upside down sine wave, negative A omega sine times omega t. By the way, I did miss something going back real quick, excuse me. This equation can also be written as x equals A cosine theta, where theta is the angular displacement in radians. That's true. This is more useful, but that's absolutely true. That's like the original equation, right? Where omega is theta all over t, radians per second, radians over seconds, and so theta equals omega t, and that's what I put in here. Okay,